Hello everyone. In the next few videos, we're going to be covering one of the most important topics in all of algebra, namely that of factoring. So we're going to start by just discussing what a factor is and what the process of factoring involves, and also explore what is known as the greatest common factor. When you write a number like 12 as a product of two other numbers, like say 3 and 4, in this manner, then 3 and 4 are called factors of 12. And 3 times 4 itself is called a factorization of 12. In general, if you have P equals A times B, then A and B are called factors of P, and A times B is called a factorization of P. We notice that each factor of a whole number goes into it perfectly, leaving no remainder. For example, 3 goes into 12 exactly 4 times, and 4 goes into 12 exactly 3 times. I also want you to note that a given number like 12 can have more than one factorization. We say 12 is divisible by 3 and 4. In fact, any whole number is divisible by all of its factors. So here are some possible factorizations of 12. The first one, sometimes referred to as the trivial factorization of 12, is when you just write 12 as 1 times itself. Now, that is a perfectly legitimate factorization of 12, and sometimes we'll be utilizing this so-called trivial factorization in our work. It's necessary to use it from time to time. Another possible factorization of 12 is when you write it as 2 times 6, or 3 times 4, which we've already seen. And then there is this one, because we never said there has to be a limit to how many factors are involved in the factorization. So here's a factorization of 12 that has 3 factors in it. Now we notice that this is a typo. This dot should be a little bit further up. That's not 2.3, that's 2 times 3. So of all of these factorizations that we see, this last one, the one where we write 12 as 2 times 2 times 3, is unique. Why? Because if it's the only one in which all 3 factors in the factorization are what are known as numbers we call prime. Now, if you recall from your previous experiences with math, a prime number is a natural number larger than 1 that is only divisible by 1 in itself. So 2 is a prime number, 2 again, of course, is a prime number, and so is 3. That's why we call this particular factorization of 12 the prime factorization of 12. It's going to play an important role in everything we do with respect to factoring from this point forward, so it's important to understand it. Let's formally remember what a prime number is again. A prime number is a natural number larger than 1 whose only factors are 1 in itself. So if you want to talk about it in terms of divisibility, you can come up with this alternate definition. You can say a prime number is a natural number larger than 1 that is only divisible by 1 in itself. That's just another way of saying the first sentence. Now, let's look at the first few prime numbers, because these are the ones we're going to be using pretty much all the time. So, but not even that many. We use maybe the first 3, 4 most of the time. Sometimes we'll encounter some of the larger ones, but rarely in our work. Note that 2 among all the prime numbers is unique. First of all, if you look at it, it's the smallest prime number. It's the very first prime number, and there's something which is really unique about it in that it's the only even prime number. Now, why would it be the only even prime number? Think about it. If there's an even number larger than 4, which is prime, then it's supposed to be divisible only by 1 and itself, but that can't be, because any even number larger than 2, say 4 even, just the very next one, is divisible by 2, so it cannot by definition be prime. So 2 is the only even prime number. We also need to recall divisibility rules really quickly. The prime numbers we have really nice simple rules for, and which we use the most often, are 2, 3, and 5. A number is divisible by 2 if it is even. That's the simplest of all divisibility rules. And of course, to be even, it means it ends in either 0, 2, 4, 6, or 8. So all these numbers that we have here as examples are all divisible by 2. All we have to do is look where it ends. That means the rightmost digit. And these, of course, all are related to natural numbers, right? A number is divisible by 3 if the sum of its digits is divisible by 3. So that means basically these are the digits, add the digits. So here we have 1 plus 2, which is 3, plus 3, which is 6. If that sum is divisible by 3, so is the number itself. Okay? Look at this, 66. So 6 plus 6 is 12, which is divisible by 3. So therefore 66 is divisible by 3. Now, here's a less obvious number. That's a huge number, and we don't have to sit there and do this really long division to see if this is divisible by 3 or not. We just need to add the digits. Notice 4 plus 0 plus 0, etc. And of course, none of these zeros are going to add anything to the sum of the digits. So all we need to worry about is 4 plus 2, which is 6, which is divisible by 3. Therefore, this number is divisible by 3. You can always try it just to convince yourself. So there's the number. We're going to go ahead and divide it by 3. And in fact, we get another whole number. It's given in scientific notation, but it is a whole number nevertheless. For 5, the divisibility rule is just as simple as it is for 2. We just look at the last digit or the rightmost digit. If it's either a 0 or a 5, then the number is divisible by 5. Next, we'd like to take a look at the prime factorization process. You might have used the so-called factoring tree. We're going to learn a more organized way of doing it now. So let's say we want to find the prime factorization of 360. So what we're going to do is we're going to write 360. We're going to draw a line to the left of it, and then we'll just start on the left side here at the same level by writing the smallest prime number that will go into 360. Of course, given that 360 is even, it's a no-brainer because we know the smallest prime number is 2, and 2 goes into 360. So we'll go ahead and write 2 over here to its left. Then we go ahead and divide. So what's 360 divided by 2? That gives us 180. We'll go ahead and write the 180 right there below the 360. Now, we repeat the process and ask the exact same question again. What is the smallest prime number that goes into 180? We know since it's even, the answer is 2 again. We'll stay with 2 as long as it works. We divide and we get 90. We write the 90 on the right column. Ask the same question again. 90, what's the smallest prime that goes into 90? Of course, that's 2. We divide again. We write the result here. Now we ask the same question for 45. This time 2 won't work because 45 is no longer even. So the likely candidates are either 5 or 3. Since 3 is smaller and we want to get a nice prime factorization on this side from small to large, we'll always try 3 before we go to 5. So in order to test for 3, we add the digits. 4 plus 5, that's 9, which is divisible by 3. So we'll go with 3. Write the 3 here. Go ahead and divide. 45 divided by 3 is 15. we write the 15 here. Again, we notice that 15 is divisible by 3, so we stay with that. We go ahead and divide, and we get 5, so we write the 5 here. Now, what is the smallest prime number that goes into 5? A more interesting question, given that 5 itself is prime, is to ask what is the only prime number that goes into 5? And remember, the answer is 5. 1 is not a prime number. If you remember the definition of prime numbers, we said any natural number greater than 1. We purposely left 1 out of the list of prime numbers because otherwise the very process we're going through right now would never end, because here I would put 1, 5, 1, 5. This process would fall into an infinite loop and it would never end. So in order to avoid that, we made sure we don't consider 1 to be prime. So the only prime number that goes into a prime number is itself. Remember that. So once you get to a prime number, just put itself on the left side, and then you'll get 1 on the right side. Now remember, on the left side, you only have primes, and because of the question we keep asking, what's the smallest prime number that goes into the number on the right? These are going to be nicely ordered from small to large, and once you're finished, and once you get to this one, that's when you know you are done. So once you get to 1, you're done. And on the left side, you have your prime factorization. So we can say 360 equals 2 times 2 times 2 times 3 times 3 times 5. Or, much more efficiently, we could use the exponential notation. We can say it's 2 cubed times 3 squared times 5. And there we have the prime factorization of 360. So very simple process, and it's a little bit cleaner than the factoring tree. I think you'll agree it's much more organized. Everything is nicely arranged, and it also takes a nice finite amount of space, which is very easy to deal with. So that's how we go about finding the prime factorization of any natural number. Here's another one. Definitely please try it on your own. It's a really important process to get extremely comfortable with. This should become second nature for you when it comes to doing math. So from this point forward, you're going to need to do the prime factorization often. All right, so assuming you've already tried it, so let's see. What's the smallest prime number that goes into 252? We know that's 2. We go ahead and divide 252 by 2, and we get 126. Now we ask, what is the smallest prime that goes into 126? Of course, that's 2. Again, because 126 is even. And we divide, so we get 63. Now we ask the question again. This time, of course, 2 is not going to work. We're going to need 3, because 3 plus 6 is 9, which is divisible by 3, so is 63. So we write the 3 here and we divide. So what's 63 divided by 3? 21. That's divisible by 3 again, so we write the 3 again and we divide. We get 7. Now 7 is a prime number. What's the only prime number that will go into a prime number? Itself. And we end up with 1 on the right side. And as soon as we hit the 1, we know that we're done. So the prime factorization of 252 is going to be 2 times 2 times 3 times 3 times 7 in spelled out notation. And if you put it in exponential notation, you get 2 squared times 3 squared times 7. So here we can do the test of it. So we'll just type 2 squared times 3 squared times 7. and we notice that we get 252. I have this decimal notation which I need to change, but this is essentially 252. Okay, I changed the settings on that. It looks nicer now. So 2 squared times 3 squared times 7 is 252. All right. So again, the process is simple. Practice it. We're going to be using it quite a bit. Now that we know how to find the prime factorization, that puts us in really great position to find the greatest common factor between two or more numbers. So the greatest common factor, we usually just call it GCF, of two or more numbers is the largest number that goes into all those numbers. That means perfectly, leaving no remainder, right? For example, the greatest common factor of 20 and 30 can be shown to be 10. Why? Because 10 is the largest number you're going to find that goes into 20 and 30. Now, you can either take my word for it, or better yet, you can look at the prime factorization of 20 and 30. Because when you do, then you'll understand exactly why 10 is the greatest common factor. So let's start on the left here with 30. We know that 2 is the smallest prime that goes into 30, and that gives us 15 when we divide. 3 is going to be the smallest prime going into 15, divide and get 5, and 5 is the only prime that goes into itself, so we have 5 and we get to 1, which tells us we're done. And on the right we have 20. We start with 2, we divide, we get 10, 2 again will give us 5, and 5 will give us 1. Now if you look at the prime factorizations, you can see they have exactly 1, 2 and 1, 5 in common. So the GCF is just going to be 2 times 5, which is precisely 10. This way you can tell beyond the shadow of a doubt that 10 is the GCF of 20 and 30. So let's come up with a process for finding the GCF of two or more numbers that can handle even larger numbers. I mean, 20 and 30 were simple. So what we'll do is we'll find the prime factorization of all the numbers involved. Then we'll write the numbers in prime factored form using exponents if necessary. Then we'll multiply the lowest powers of only the common factors to obtain the GCF. So you can see that with 20 and 30 very simply. So with 20, remember we have 2, 10, 2, 5, 5, 1. With 30, we had 2, 15, 3, 5, 5, 1. So now we're going to write 20 as 2 squared times 5, and we're going to write 30 as 2 times 3 times 5. So remember, now we're going to multiply the lowest powers of only the common factors. So we need to first isolate the common factors. We can see that 2 and 5 are the only common factors. 3 is not. So we don't even consider 3. So to get the GCF, we multiply the lowest powers of the common factors. So the GCF is going to be, so look, between 2 squared and 2, which one is the lower power? 2, right? And between 5 and 5, which is lower? Where they're the same, so you just write 5. And that's how you get 10. So this is the procedural way, the algorithmic way of finding the GCF. Let's try it with some larger numbers. I think you'll remember these two numbers from before. We've seen them. So let's go ahead and quickly do the prime factorizations again. So for 252, I definitely recommend you try this on your own. Find the GCF, then come back to join me. So we'll come back. 2 gives us 126. 2 gives us 63. 3 gives us 21. 3, 7, and 7, 1. Now for 360, we start with 2, which gives us 180. 2, remember, at each step you ask yourself a simple question: what's the smallest prime number that goes up to, in the number on the right? So for 180, it's 2 again, we get 90. Again, 2 gives us 45. This time we have to go to 3, which gives us 15. 3 again gives us 5, and 5 gives us 1. So we can write 252 as 2 squared times 3 squared times 7, and we can write 360 as 2 cubed times 3 squared times 5, right? So first we're going to run through the process, which, remember, we're going to multiply the lowest powers of only the common factors to get the GCF. So our GCF, all right, so let's locate the common factors first. Notice this time also we have 2 and 3 as our common factors. So looking at 2, powers of 2, we're going to pick the lowest power of 2. So between 2 squared and 2 cubed, which one is the lower power? 2 squared. And between 3 squared and 3 squared, which one is the lower power? Again, they're equal, so take either one. So you have that. So basically you have 4 times 9, which is 36. Now that's going to be the larger number, the larger factor that goes into both of those numbers. You can try that out and verify that. Notice 252 divided by 36, that gives us 7. 252, I'm sorry, we did 252, so this time we want 360. Of course, we know that 360 divided by 36 is 10. That works too. So the really nice feature of prime factorization is how it can give us a nice procedure for finding the GCF of 2 or more numbers. Okay, now we're going to go ahead and find the GCF of these 3 variable expressions. We'll go ahead and treat them in a very similar manner. We'll go ahead and start by finding the prime factorization of the constant coefficients. So 20, we know 2 goes into 20 10 times, 2 again 5 times, and then 5 once. For 35, we know that 5 goes into 35 7 times, and then 7 goes into itself once. For 15, we know that 3 goes into it 5 times, and 5 goes into it once. So if I rewrite these using these prime factorizations, we have something like 2 squared times 5 x squared y cubed z to the 4, and then we have 5 times 7 x to the 4 y squared z squared, and then we have 3 times 5 x cubed y. We recall the procedure for finding the GCF, which is to multiply the lowest powers of only the common factors. So when we look at these 3 expressions, we can see we'll start by just writing what the common factors are. Then we'll worry about the lowest power. So the common factors seem to only be 5, right? If you notice, they all have 5s in common. And we notice that there's also x in common, right? So that's a common factor. We're not dealing with the powers yet, just the variable whose power is going to be a common factor. And so let me go ahead and use double bars for those. And I'll just go ahead and use green for the next one, which is going to be the powers of y, right? So those are common factors too. So basically, our GCF is going to have a 5 in it. It will have some power of x in it and some power of y in it. Now z is not in the last a factor in the last expression, so it's not a common factor, so it's not even going to be part of our GCF. So for 5, we look for the lowest power that we see, and we see that's just the first power itself, right? For x, this one is x squared, this is x to the 4, and this is x cubed, right? So which one is the lowest power? As you can see, it's the x squared. And for y, we look at y cubed, y squared, and y, right? So of those 3 that we have marked in green, which one has the lowest power? Obviously the y itself, because as we know, there's an invisible 1 there, so that's going to be the lowest power. So our GCF here is going to be 5x squared y. And that's how you handle something like that. How about this one? 25xy and 36uv. What would be the common factor of those two expressions? Well, we know 25 factors as 5, 5, 5, 1. So 25 we know is 5 squared. For 36, we have 2, 18, 2, 9, 3, 3, 3, 1. So 36 is 2 squared times 3 squared. Notice there's no common factor here, but always remember any two numbers have a common factor. In the worst case scenario, it's 1, right? So the GCF of the numbers is 1. Notice x, y, and neither x is common to both terms nor y, nor u, nor v. So the only common factor for these two expressions is 1. So we say the GCF is 1. When this happens, either between just two numbers, even if we were just looking at 25 and 36, or two expressions like this, we say the two expressions are relatively prime. Relatively prime. Remember, it doesn't mean either one is prime. It just means with respect to each other, they have no common factor other than 1. So now we actually get to the part where we're going to be factoring expressions. So what is the whole process of factoring and what does it mean? Well, it's basically taking any number or any expression and writing it as a product. See, when we go 3 times 4 equals 12, here we're multiplying. If we take the same equation and write it as 12 equals 3 times 4, we have done what's called factoring. So it's the reverse process of multiplying. So here, for instance, if I write x times x plus 2 and I distribute the x, I get x squared plus 2x. Here we call this process multiplying, right? But if we start with the x squared plus 2x and realize that, hey, I can write this as x times x plus 2, then what we have done is called factoring. So to write as a product of two factors is the process of factoring. And this is what we're going to be doing for quite a few videos now. the first type of factoring we're going to study when it comes to expressions is factoring out the GCF. The process which helps us accomplish that is, if you recall the distributive property, we have A times B plus C. Remember, we distribute the AB plus AC like that, right? So if we do this backward, go from right to left, start with AB plus AC, look for what's common, A, write that on the outside, and then open parentheses and see what's left. You put the B plus C. That process, in other words, these two statements are saying the same thing, but this one is saying it in the multiplicative direction, this one is stating it in the factoring direction. So when we take the common factor out, A, from these two terms, what are we left with? B plus C. That's basically the essence of factoring out the greatest common factor. Let's try it here. So we look at these three terms. First thing we do is we look for the GCF. This is pretty simple. We know that for the numbers, the GCF is just 5. And for the powers of x, right, we look for the lowest power of x, and that's just x, right? So we can see that the GCF is 5x. So we go ahead and factor it out like this. Then we can either divide 5x cubed by 5x to see what needs to go here, or we can just reason it out. We can say 5x times what expression will give me 5x cubed. You see what I mean? In one case you're dividing, in one case you're asking what to multiply, which are going to end up giving you the same result. It's probably a little bit easier to do this when ask the question when they're simple, and when they get more complex it might be easier to do the dividing. So for now, what do we need to multiply 5x by so that we get 5x cubed? Of course, you know that has to be x squared. And what do we have to multiply 5x by to get 10x squared? Notice that would have to be 2x. And what do we have to multiply 5x by to get this? Well, just carry the sign, the negative, and of course you're going to need just a 5, right? Right now you have factored out the greatest common factor of this expression. Now, how do you check factoring? By multiplying. So you want to check it, just multiply 5x by x squared plus 2x minus 5. See what you get. Notice you get 5x cubed plus 10x squared minus 25x, which is what you started with. So it works out. Now, if it's hard for you to see where these come from, then divide. Look, write the GCF, then to find out what each of these terms is going to be, divide that term by the GCF. So the next one will be 10x squared divided by the GCF. Oops, by the GCF. Let's not make a mistake there. The GCF is 5x. All right, so the alternate way of doing this is to take out the GCF, then divide each of these terms by the GCF, each of the three original terms by the GCF to see what should go here. Notice what's 5x cubed divided by 5x? That's x squared. What's 10x squared divided by 5x? That's going to give you 2x, right? And what's 25x divided by 5x? That's where the 5 comes from. So if you can't do this in your head and you need to see more work, show this work. Write the GCF, then divide each of the original terms by the GCF to see what should go here. All right? And that's how you can do it with more support. Let's try this one. Now, usually when your lead term has a negative number in it, a negative coefficient, we tend to want to factor out the negative as well. This is called factoring out the negative. So if we were to find the GCF for these two terms and take out the negative with it, we would get negative 3. What's the lowest power of x that you see in common? X squared, right? And for y's, it's going to be y squared. So now we take it out, right? And what do you need to multiply this by to get this term? You see that? All you need is an x, right? That's all that's needed. And what do you need to multiply negative 3x squared y squared by to get this term? Well, first of all, to get a positive, it better be negative, right? And to get 9, you're going to have to multiply the 3 by 3. X squared is already there. We don't need to do anything. And what do you have to multiply y squared by to get y cubed? Just the y, right? And that's it. You just factored out the negative. Remember, another way you could have done this is to write the common factor, the greatest common factor, and then just divide each of those original terms by the factor you've taken out. Like so. And you'll see, you'll get exactly those two terms when you do so. Negative 3 over negative 3, that's just 1, so the coefficient is 1. X cubed over x squared gives you the x. The y squares cancel out, so you just get x, right? Positive divided by negative, that gives us a minus here. 9 over 3 is 3. The x squares cancel out. Y cubed over y squared is y. Normally, we don't show this, but if you need to, then you show it. If you tend to make mistakes doing it in your head, show the work. There's no shame in that. Okay, what if we were to find the GCF of this expression and factor it out? Notice, what is the greatest common factor of this expression? What do these three terms have in common? Well, obviously, one of them is 1. So there's no way we're going to do better than 1. So the GCF is 1. So if you were to factor out the GCF, you would just put a 1. It would look like this, right? Now, this is a redundant process which we usually will not do, right? So when they say factor this, usually we'll just leave it like that and we'll say this expression is prime. Because remember, when you find for a number like say 7, since all you can do is write it as 1 times 7, or of course 7 times 1, 7, same thing. In other words, since its only factors are 1 and itself, we say 7 is prime. Well, the same goes with an expression. When you have an expression or a polynomial whose only factors are 1 and itself, we say it's a prime. We say this is a prime polynomial. And again, we usually will not show this factorization. We'll just choose this option. We'll just say this is a prime polynomial. Now, sometimes the common factor between two terms is not just a monomial, but rather a binomial. So let's look at some of those examples. So first of all, notice here that many students are confused about how many terms we have here. Remember, the signs that determine a separation between terms are those that are outside of all grouping symbols. So the only sign in this problem that's separating terms is that sign. So this whole product here, 2y times x minus 3, this is considered one term. And this is considered one term. In fact, as long as you have a multiplication going on, like let's say I have x times 2x plus 1 times 3x plus 1, and let's say I just keep this pattern going. I go times 4x plus 1, and I have a lot of time and I'm bored, so I'm going to do this till the end of time, right? Of course, I'll never run out of numbers, right? Because there's always a next number, 5, 6, 7, right? But if I have as many factors of this as you can possibly imagine, right? And I stop at some point, that's still going to be one term. You understand? Multiplication of factors like this doesn't create new terms. Now, let's say I reach the end of the universe, right? Then at that point, when I reach the end, I put +1, right? Right there, that plus right there will add a new term. So now I have this one gigantic term, and I have this one tiny term, but I now have two terms. So as long as you're multiplying factors, you still have just one term. So that's one term, and that's one term. So we have two terms in this expression. Now, what is the common factor? Well, you can see the common factor is x minus 3. That's why we said we have a binomial GCF. So now we're going to factor out the x minus 3 and see what's left. So when we do that, what do I need to multiply x minus 3 by to get this term? You notice? What's missing? 2y. Plus, and what do you have to multiply x minus 3 by to get this term? What's missing? 5. And that's how you factor out a binomial GCF. It doesn't even have to be a binomial. It could even have 10 terms. So we should, generally say that's how you factor out a polynomial GCF. But most of the time, the type we're going to encounter are going to be binomials at most. All right, so here's another example. Definitely try it on your own before you come back to the video. Okay, so again, you can see the total number of terms is just 2 terms. That's one term and that's one term, for a total of 2 terms. These 2 terms have a common factor. What is it? It's definitely that part, but notice this one does a little more than that. There's also a common factor of p. So the GCF of these 2 terms is going to be not just 3 cubed plus 1, but also what's the lowest power of p that they have in common? The first power. So it's actually p times 3 cubed plus 1. Now, when you factor that out, what's left? In other words, what do you have to multiply this by to get this, right? You see that? It's only p. Plus, and what do you have to multiply this GCF by to get this term? Notice the only thing missing is what? 5. And now you have completely factored that. I factored out the GCF, the binomial GCF of these 2 terms. All right, the last thing we're going to do in this section is another technique of factoring. It's called factoring by grouping. Usually applies when you have an even number of terms. Not always, but most of the ones we're going to encounter are going to have an even number of terms. So let's have a look at 1 or 2. All right. So if you look at these 4 terms in this problem, you'll notice that if I were to look for a greatest common factor among all the terms, I would not be able to do better than 1. It would be the greatest common factor of all of them is 1. But I noticed that if I, instead of looking at all of them, I just take a look at 2 of them at a time, I can do better as far as the GCF is concerned. Like, for example, if I were to look at these 2 terms, and then those 2 terms. So I'm dividing it into 2 groups, right? So I noticed that in the first group, I have a GCF of y, right? So I go ahead and factor out that y, and that will leave me x plus 5, right? And I noticed that in the second group, I also have a GCF of 2. So here it's very important that I write the plus, because we don't want the process to turn from this sum into suddenly a multiplication. And then I write the 2, which is the GCF, and I take out the 2, and that leaves me x plus 5. Now I notice that I have gone from 4 terms to 2 terms, and I notice that these two new terms have a common binomial GCF right there. So I go ahead and factor that out, and that leaves us y plus 2. So this is how we accomplish what's called factoring by grouping, okay? And that right there is where we leave this. All right, so here we have another example. Go ahead and give this a try before you come back. There's a little point in it that I'm hoping you'll catch. All right, welcome back. Notice in the first two, if we just group them like this, those two and then those two, in the first two terms we have a common factor of, you guessed it, 2u. If we factor it out, that leaves us what? U minus 2, right? Now in the second group we have a common factor of 3v, right? But because that first one is negative, we'll go ahead and factor out the negative with the 3v. So instead we'll factor out negative 3v. So let's see what that will leave us. What do we need to multiply negative 3v so that we get negative 3uv? Notice all that's missing is u. And what do we have to multiply negative 3v by to get positive 6v? Notice we do need a negative, so that negative times negative becomes positive, and we need a 2 so that 2 times 3v will give us 6v. Great. Now we notice that firstly we've gone from 4 terms to 2 terms, and we also notice that we now have a binomial GCF. We factor it out, and that leaves us 2u minus 3v. Notice how many terms we have now. In the last step, we have exactly 1 term. In fact, this 1 term situation where it just becomes a product of a bunch of factors is the very goal of factoring. It's a process of term reduction. We go from 4 terms to 2 terms to 1 term. Now you'll see later why this is so important to us, because we're going to be able to solve equations with this process. But for the time being, just notice that we're reducing the number of terms till we just get 1 multiplication involving factors. That's the essence of factoring. Go ahead and try this one, see what you get for this, and come back. All right, welcome back. Notice we have, if we pick these 2 terms, right, and then those 2, so in other words, if we group it like so. In the first 2 terms, we have a common factor of 3x, but we'll go ahead and take the negative 3 with it, the negative with it. So negative 3x, that will leave us what? You know, you can play this like a game. Look at this, look at this. What's missing from this? See what's missing? Just y. That goes here. Now, how do you get from negative 3x to negative 9x? What's missing? Just the 3? That's right. And notice it better be positive, because otherwise when you distribute it, right, if you put a negative here by mistake, when you distribute the negative 3x, you would get positive 9x. That's not what you want. You want negative 9x. So you want to make sure that's positive 3. All right, so now we go over here. What's the greatest common factor? Well, yeah, you said it. It's 1. Now, normally, right? Normally, we don't show factoring out a 1, right? Well, this is one exception where it'll be helpful to do it. Because now you notice we get plus 1 times y plus 3. It's more clearly stated that we now have 2 terms. These 2 terms. So from those 2 terms, we're going to factor out the GCF, which is that binomial factor, right? So when we factor out that binomial factor, that leaves us negative 3x plus 1. You leave it like that. Sometimes some people don't like starting an expression with a negative if they have a choice. And you may actually see the answer like this. They'll switch this up. And instead of negative 3x plus 1, you may see 1 minus 3x. So they're both correct. So this or this. All right? So that's how you do these factoring by grouping problems. All right, and here's the last one for the road. I just wanted to show you this one because sometimes the original arrangement of the terms may not work out, but that doesn't mean we should give up right away. Like, if I just broke it down like we normally have been doing in the last few problems as this group and this group, well, what's the greatest common factor of this group? It's just 1, right? Doesn't do us a whole lot of good. And how about this one? A, okay, yeah, you can take out an A, but that just leaves you 3 plus B. That doesn't do a whole lot of good either. So we can always rearrange. Remember, you can, let's say you have A plus B minus C minus D. You can always rearrange those as much as you want, as long as each term keeps the sign that it has on its left, because that's its sign, right? So for example, let's say I want you to rewrite it so that you start with negatives, right? So you could go negative C minus D. Notice how both of them kept their sign, and then plus A plus B, like that. Let's say I want you to put it in reverse alphabetical format. So then you would just go negative D, negative C, plus B, plus A. These are all the same. They're all the same value. So as long as the term keeps its sign, it can move anywhere in an expression. So here we can rearrange this to where we have A squared and 3A next to each other. And also we have 3B and BA next to each other. So we just rearrange the terms. Now these groups look more promising. The GCF of the first group here is A. We factor it out. That leaves us A plus 3. And the way this works is as soon as you notice that, oh, I got it from here, that's when you pause the video, go finish it on your own. I cannot overemphasize how important it is for you to get actively involved in this if you want to make some serious progress in mathematics or in any other subject field. It's when you figure things out on your own that you make progress. So for the next 2 terms, the GCF is B. So we factor out the B, that leaves us 3 plus A. Now you may say, oh, we don't have a GCF, but we in fact do, because remember, A plus B equals B plus A for all real numbers A and B. This is called additive commutativity, right? Or the commutative property of addition. So the order doesn't matter. A plus 3 and 3 plus A are the same thing. So we go ahead and factor out that. And we can write it as either a plus 3 or 3 plus a, but we'll just go with a plus 3. And when we factor it out, it leaves us a here and b here. And now we are done. Okay? If you want to check it, you can always check it, like just multiply it out. So let's use a table to do that. Remember those tables? So we have a plus 3, a plus b. If we multiply it out, what do we get? We get a squared plus ab plus 3a plus 3b, right? So if we actually write it out, we have a squared plus ab plus 3a plus 3b, right? Notice it doesn't look identical to this yet, but if I just rearrange the terms, you can see all the terms involved in the original problem are there, right? There's a squared, there's ab, which is the same as ba, there is 3a right there, and there's 3b. So it checks out. So that's how we handle factoring by grouping, and we've seen the different scenarios and curves in the road at this point. Okay, so make sure you practice all these and stay safe till our next video.